At any given moment, about 1,800 thunderstorms are in progress somewhere on the globe. New observations by NASA's Fermi Gamma Ray Space Telescope show that thunderstorms make antimatter. The process starts with a terrestrial gamma ray flash, or TGF, an intense pulse of gamma rays originating from thunderstorms. These dots mark TGFs observed by Fermi's Gamma Ray Burst Monitor during the spacecraft's first 8 months of operations. Researchers estimate that there may be as many as 500 TGFs each day. On December 14, 2009, as Fermi passed over Egypt, it spotted a TGF produced by a thunderstorm in Zambia. The TGF was over the spacecraft's horizon, where Fermi couldn't see it. So how could Fermi have detected it? Scientists believe that the TGF process begins in a thunderstorm's intense electrical field. Electrons within this field become accelerated upward. Above the storm, where the air is thin, the electrons can ramp up to speeds nearly as fast as the speed of light. When these ultra-fast electrons encounter an atom, they emit gamma rays. Very rarely, one of these gamma ray photons grazes an atom and transforms into a pair of particles. One, an electron, is normal matter. The other is antimatter, the electron's opposite, called a positron. The gamma rays travel in straight lines, but the charged particles spiral along lines of Earth's magnetic field. And that was the route to Fermi. The particles created by the TGF rode upward on magnetic field lines and then struck the spacecraft. The positrons annihilated when they struck electrons in Fermi, creating a flash of gamma rays. For an instant, Fermi became a gamma ray source and set off its own detectors. A fraction of a second later, some of the particles were bounced back along the same magnetic field line. They again passed through Fermi and again produced gamma rays. The spacecraft has observed this phenomenon on at least 4 other occasions. So the next time lightning flashes and thunder roars, remember, you may be witnessing antimatter in the making.
Convective storms hold an extraordinary surprise. Under just the right conditions, they fire off some of the highest energy light naturally found on Earth, terrestrial gamma ray flashes, or TGFs. Rising and falling snow and ice particles repeatedly collide, filling the cloud with electrical charge. Once the electric field is strong enough, a current flows and a lightning flash occurs. The flash produces an abrupt reconfiguration of the electric field. In some cases, a surge of electrons rushes toward the upper part of the storm at speeds nearly as fast as light. When deflected by air molecules, these accelerated electrons give off gamma rays, producing a TGF. Data from NASA's Fermi Gamma Ray Space Telescope suggest more than 1,000 TGFs occur each day all over the globe. For the first time, improved data link dozens of TGFs to specific tropical weather systems. Tropical storms far from land tend to generate less frequent lightning. Nevertheless, observations show they are surprisingly prolific producers of TGFs. Tropical storm Manuel made landfall just shy of hurricane strength. As it rapidly weakened, it produced 2 TGFs within 24 hours. More typically, TGFs are associated with the strengthening phase of a storm. As Typhoon Bolivan rapidly developed in 2012, thunderstorms nearly 500 miles from its center launched a TGF with 4 distinct pulses. So far, the record holder for TGFs is the rapidly strengthening tropical wave that later gave birth to Hurricane Julio. It produced 4 TGFs within 100 minutes. A 5th followed the next day, with nothing further. What scientists learned so far is that weaker tropical storms are capable of producing more TGFs, and those events can arise anywhere in the storm. For stronger storms, like hurricanes and typhoons, TGFs are more common in the outer rain bands, which host the highest lightning flash rates in these storms. The findings provide new insights into the relationship between storm intensity, lightning frequency, and TGFs. This adds another important piece to the puzzle of our understanding of TGFs and how they are created in thunderstorms, the most powerful natural particle accelerators on planet Earth.
When we talk about the global electric circuit, we are describing how electricity naturally flows throughout Earth's atmosphere. It can be generated by the interaction of solar wind with Earth's magnetic field, down to the electricity that individual clouds produce. Clouds that produce lightning in a thunderstorm, for instance, feed electricity into the global circuit also. They're all a part of the same system. Could the amount of electricity in the atmosphere change the way clouds and storms develop? Could cosmic rays impact atmospheric electricity and the severity of winter storms? By doing basic research and creating computer models, scientists hope to answer these kinds of questions, and perhaps find answers to questions we haven't even thought to ask yet. Blue jets shoot out of electrified clouds with or without lightning. Most of all, they want to know how to represent these interactions mathematically in a model of the system, and that's not easy. We use math to represent natural phenomena like how much energy Earth receives from the sun, and the weather that emerges as a result. By taking these things we know and translating them into a mathematical model, we can build a pretend Earth, a model to test things that we never could in the real world. Trying to create a model for the global electric circuit presents incredible challenges. First of all, studying the global electric circuit requires experts across many areas. Scientists who specialize in the uppermost atmosphere, solar wind, electromagnetism, chemistry, the physics of lightning, cloud formation, volcanic weather, and more. Secondly, the model is trying to encompass events that are a part of the global electric circuit on vastly different time and spatial scales, from sprites that appear for a few milliseconds to the 11-year solar cycle, or enormous events like gamma-ray bursts down to small particles that influence cloud formation and cloud electrification. And there's even uncertainties about how clouds are charged and how atmospheric conductivity occurs and breaks down. So what is the global electric circuit? It's a system that encompasses all of the electrical generators, currents, and TLEs in Earth's atmosphere. Because of observations, satellites, ground-based networks, and observations of electrical phenomena between clouds and the ionosphere, we know a lot more about Earth's global electric circuit that traverses Earth's upper and lower atmosphere, but we still have a lot to discover about the system. Basic research will help us get the answers we seek.